everyone. So today we are going to talk of classification of hydrocarbons, functional groups, and what are the various types of functional groups you will find across organic chemistry. So how did we arrive over here? So if you have already watched my previous video where I talk about the introduction to organic chemistry, where it stands in the field of chemistry, and why the particular reason as to why carbon is the star in organic chemistry, and the various fields in which organic chemistry is daily used in our day-to-day lives. And with that, we have already come to classifying hydrocarbons. So when it comes to hydrocarbons, you might wonder, okay, so this word, when you hear it, there's nothing to wonder. You already know, you can already figure out actually what a hydrocarbon is. It's a compound containing, obviously, hydrogen and carbon. But now you might actually wonder, does it mean that only carbon and hydrogen are the only elements you're going to find in organic compounds, or are there any other compounds? So actually there are other compounds, which means carbon and hydrogen are not the only type of elements you will find under organic compounds. So if you can remember as the particular reason to why carbon is a star or the star in organic chemistry, I have already talked about the most prominent type of bonds you would find throughout organic chemistry is carbon-carbon and carbon-hydrogen bonds, which is why at the very beginning we learn about the classification of these compounds that contain carbon-carbon and carbon-hydrogen bonds. So we have given a particular name for these compounds as hydrocarbons. But at this stage, I would also like to mention that there are other compounds. So which means there could be other elements also joined in these organic compounds, where at that instance you call them heteroatoms. For example, it could be oxygen, nitrogen, or halogens such as fluorine. So when it comes to different compounds, we need to have another classification in order to categorize these compounds, which obviously are non-hydrocarbons in that case. Or even if it's hydrocarbons, we need to know what sort of other ways we can classify them. So another way in which organic compounds can be classified is through functional groups, which you are going to learn very next in this video as well. But before that, let's actually talk about hydrocarbons. So once again, hydrocarbons are compounds containing carbon and hydrogen. And as you see here, hydrocarbons can be classified into two main branches as aliphatic hydrocarbons and aromatic hydrocarbons. So unlike you hearing the word hydrocarbon, now it's going to get a little serious because now there's new vocabulary introduced to you as to the words aliphatic and aromatic. So the word aliphatic and aromatic, the very common thing that you know by now about these two compounds is the fact that obviously they contain carbon and hydrogen. So I would like to mention that I have taken this classification as well as this table right here, where aliphatic and aromatic hydrocarbons are differentiated according to certain properties. So these two images are taken from two different websites, which I have attached the link in the description of this video down below, so you can refer those with websites as well. But apart from that, in order to summarize and give it to you point wise the structure of this lesson, I have picked out those two images and attached right here in this video. So coming back to aliphatic and aromatic hydrocarbons, now I say the very similar thing that you're going to note is that obviously they both contain carbon and hydrogen. So what exactly is different among the two? The main difference, let's talk when it comes to the structure, because the particular structural reason is the reason as to how this classification is mainly done. So hydrocarbons, there's aliphatic hydrocarbons. And under that, obviously, as you can see, there's carbon and hydrogens bonded together in a certain manner. And in the branch where you find chain-like structures, you can call that certain branch as acyclic hydrocarbons. And on the opposite branch where you contain cyclic structures, you can call them cyclic hydrocarbons. Whether it's acyclic or cyclic, they're still under hydrocarbons, and these two branches are under the certain branch called aliphatic hydrocarbons. So, as the name suggests, they contain carbon and hydrogen, and in this case, now you know they could contain sigma bonds among each other or pi bonds as well, and they are linear structures, or they even could be cyclic structures, and also they could be branched as well. I will explain to you how branching occurs, but before that, let's just know that under aliphatic hydrocarbons, they could be linear, they could be branched, or they even could be cyclic, but somehow they also could be containing carbon sigma bonds and carbon and hydrogen sigma bonds, as well as carbon and carbon pi bonds. So what's different among these structures and aromatic hydrocarbons? Now, when it comes to aromatic hydrocarbons, even they obviously contain carbon-carbon, carbon-hydrogen bonds. But apart from that, they do also contain sigma bonds, just like aliphatic hydrocarbons. And they also contain pi bonds as well, as you can see here, whether it's benzenoid structures or non-benzenoid structures, which are the two branches you meet under aromatic hydrocarbons. They would contain, or they do contain carbon-carbon sigma bonds, carbon-carbon pi bonds. The main prominent factor when it comes to aromatic hydrocarbons is the fact that there's resonating single and double bonds in aromatic hydrocarbons. This gives a property called conjugation. Under aliphatic, for structures, you can say carbon atoms are joined with hydrogen atoms. They could be either linear or branched or even cyclic, as we saw before. And electron delocalization is not possible here, meaning there's no conjugation, meaning there are no resonating single and double bonds when it comes to aliphatic hydrocarbons. But even if there's resonating single and double bonds, there's no particular delocalization of electrons. But when it comes to aromatic hydrocarbons, just like aliphatic, they are linked with carbon and hydrogen elements via sigma bonds, and there are pi bonds as well, but in this case you're going to come through electron delocalization due to their cyclic and planar structure. So there are other properties as to how you can differentiate among the two categories, but before we move on to the rest, I would like to come back to this chart and talk about the structures individually. So once again, hydrocarbons divided into aliphatic and aromatic hydrocarbons, and under aliphatic you're going to find acyclic hydrocarbons and cyclic hydrocarbons. So before talking about acyclic hydrocarbons, I would like to finish off cyclic hydrocarbons, because now when I say cyclic, obviously you're going to imagine cyclic structures as I have depicted in this photo. So cyclic structures, now you're going to notice that there's two different types of depictions for the same molecule. So when I say cyclopropane, cyclobutane, cyclopentane and cyclohexane, they're cyclic structures, which is why you find the prefix cyclo in front of the particular name of the compound. And the two depictions are actually two different types of ways or different formulae in which you can represent a particular organic molecule. So these sort of molecules are represented in the format of a condensed structural formula. So they are actually dash formulas, which means you have lines that show the bonding electron pairs, and they include elemental symbols for all the atoms in a molecule. But in this case, the R dashed formula, but as you can see, you can only see the bonding between carbon and carbon. You are not represented with the bond between carbon and hydrogen. So, which is why I actually call them condensed structural formula, which are faster to write than dashed formula, as the hydrogens are attached to a particular carbon and are usually written right after the carbon. So, by now you know that the valency of carbon is 4. So, it needs to gain 4 extra electrons in order to complete its outer electronic shell. Now, with that, it needs 4 bonds around it, whether it's sigma or pi, it somehow needs to have 4 bonds. So in this case, you would see this carbon and this carbon, 1 bond. This carbon and this carbon, another bond. And there's 2 hydrogens, which means this carbon is joined to a hydrogen on this end, hydrogen on that end. Remember, this is condensed structural formula, so the 2 hydrogens are condensed over here. Now, in this case, it's cyclopropane. Prop meaning there's 3 carbons, so you're going to see this sort of a bonding among the 3. Now, another depiction which you can show the same structure is through bond line formula, which are, as you can see, this triangle, this square, and all these other shapes. So it doesn't necessarily mean that it's a triangle or a square. It just simply means a bond line formula where the lines represent a bond and the bend. So in this case, as you can see, there are 3 bends. So which means the bend represents carbon atoms. So there's 3 carbon atoms. And the number of hydrogen atoms on each carbon is assumed to be the maximum number of hydrogen atoms present. So for example, if you have a carbon at this particular point, you're going to see 1 bond, another bond, and obviously it needs 2 extra bonds. So this particular carbon over here is, in your head, you need to imagine that it's actually connected to 2 extra hydrogens. And another particular fact about bond line formula is that elements other than carbon and hydrogen are shown with its particular symbol. So when it comes to carbon and hydrogen, they are not represented in bond line formula, and you're just going to see shapes like this. And once again, cyclobutane, but meaning there's 4 carbons, pentane, pent meaning there's 5 carbons, and cyclohexane, hex meaning that there's 6 carbons. So these are closed chain or cyclic hydrocarbons which come under aliphatic hydrocarbons. Now, the other branch where you find acyclic structures is open chain, which means once again they could be linear or they could be branched. But under acyclic hydrocarbons, you are going to meet saturated hydrocarbons as well as unsaturated hydrocarbons. So what does saturated and unsaturated mean? So just like as the name suggests, saturated means it's full. It means simply it contains the maximum number of hydrogen atoms that the carbon compound can have. So for example, under saturated hydrocarbons, you meet the alkane family. So you're going to have carbon, and this carbon is going to be full. As the name suggests, it's going to be saturated, which means around this particular carbon, it's going to have the maximum number of bonds that it can particularly have. So what's the maximum number of bonds that carbon can make? It's 4. So it's going to be carbon connected to 4 other atoms. It could be another carbon, it could be another hydrogen. In this case, it's only carbon and hydrogen, simply because we are talking about hydrocarbons. Now, this carbon connected to another carbon, 1 bond. This carbon and hydrogen bond, another bond. This carbon, hydrogen, another bond. This carbon and hydrogen, another bond. So altogether there's 4 bonds around this carbon, and the same appears to the other carbon on the other side as well. This structure is ethane, eth meaning that's 2 carbons, and ane meaning that it's an alkane. So the suffix ane is representing the alkane family, and the prefix represents the number of carbons. And these are once again saturated hydrocarbons, which means that every carbon is full with the maximum number of bonds that it can have around it. And now you're going to meet unsaturated hydrocarbons, which means simply that the carbons are not going to be full in this case. Carbon-carbon double bonds, in this case, these compounds containing carbon-carbon double bonds are known as alkenes. And the prefix "ene" will represent, so ethene. Ene representing that it belongs to the alkene family, eth representing that it has two particular carbons. And in this case, the carbons are going to be unsaturated. The compound is going to be unsaturated. So this carbon right here will not have the maximum number of hydrogen atoms that it can bond to. But it doesn't mean that it will not have 4 bonds around it. It still has 4 bonds around it. So as you can see, this carbon and this hydrogen, 1 bond. This carbon and this hydrogen, another bond. This carbon and this carbon, 1 sigma bond, and this carbon and this carbon, another pi bond. So altogether there's going to be 4 bonds around this carbon, just like in this previous case where we talked about the first carbon under ethane. But the only difference is that it's not going to have the maximum number of hydrogen bonds it can have. Hydrogen bonds in the sense carbon-hydrogen bonds. So this carbon and this hydrogen, 1 bond, another bond, but it can actually have another carbon-hydrogen bond, which in this case it does not have. Instead, it has a pi bond. So you have 1 sigma, 1 pi bond, meaning a double bond, which comes under the family alkenes. And under unsaturated hydrocarbons, you will meet alkynes as well, where you will meet carbon-carbon triple bonds. So with the alkyne, the prefix representing, in this case, in this example, it's eth, meaning there's 2 carbons, and the suffix "ine" representing that it belongs to the alkyne family. So with the triple bond, you're going to meet 1 sigma bond, 2 pi bonds, and still carbon will have 4 bonds around it. So which is, in this case, the number of hydrogen atoms would only be 1. So this particular carbon is bonded to 1 hydrogen atom, another carbon atom, and through a triple bond. So still has 4 bonds around it, but not the maximum number of hydrogen atoms it can have. Therefore, it's going to be unsaturated. Now, just talking about these structures, as you can see, so I kind of have represented these hydrogens in a particularly different way, rather than just drawing a dash among the 2 elements to represent the bond. This is going to be a dashed bond, and this is going to be a wedged bond. So these are another type of formulae where you can represent the 3D nature of these sort of molecules. So the fact that this is just a single line between this carbon and this hydrogen, meaning that it comes on the plane, while this is also a single line, meaning that this carbon-carbon double bond is also on the plane. On the other hand, this carbon and this hydrogen is bonded through a dashed line, which means that it comes behind the plane. So it actually goes through the plane to behind. And this carbon and this hydrogen is, it appears in a wedged line, which means it comes towards you. So as you know, alkanes have carbons which are sp3 hybridized. So you will learn about these hybridizations under the lesson 2, structure and bonding, where you talk about how to find out the hybridization of particular compounds. So with that knowledge, assuming that you are good with that, I'm talking alkanes have sp3 hybridized carbons, and which means that it's going to have 4 sigma bonds around it. So all these are sigma bonds, except that so the number of Vesper units around it is going to be 4. So it's going to have the tetrahedral structure. So these 4 sigma bonds are going to be arranged in a tetrahedral manner, where 2 of them appear on the plane, while one bond goes behind the plane and one bond comes towards you, like outside of the plane. And since it's a tetrahedral structure, you're going to meet the angle 109.5 around 2 carbon hydrogen bonds. Now, moving across from alkanes to alkynes, another specific thing that you're going to notice is the fact that it's going to move from single bonds to double bonds to triple bonds. So going from single to double to triple, as you can see, the bond length decreases. So when the bond length decreases, the bond strength increases, which means that the triple bond is going to be the strongest. Then the very next strongest is going to be the double bond, and the least strongest is going to be the single bond among these acyclic hydrocarbons. So that's about acyclic hydrocarbons. At this stage, I'm just giving you a rough idea about the structures and the classifications. So later on, we will move on to the families. Alkanes, what sort of reactions it has, what sort of properties it has, and how do we name alkanes. Same goes for alkenes, same goes for alkynes. So likewise, we will talk about them differentiating among the families later on, taking or in considering the homologous families individually. But for now, let's just have the rough idea. So that's all about aliphatic hydrocarbons. Now, moving on to aromatic hydrocarbons, again, coming back to the beginning, they are still hydrocarbons. They still do contain carbon-carbon hydrogen bonds, and the only difference is the fact that there's electron delocalization in the. So, aromatic hydrocarbons having the electron delocalization can be categorized once again into 2 branches. One is benzenoid structures and the other is non-benzenoid structures. So under the GCE A-level syllabus, you're only supposed to know that aromatic hydrocarbons will contain benzene-like structures. So, but the actual fact is that there's 2 types of categories, benzenoids and non-benzenoids, where under benzenoids you will find benzene and its compounds, which belong under aromatic hydrocarbons. And under non-benzenoids, you will not meet the benzenoid structure, yet it is still aromatic. So what does this benzene structure means? So this is the benzene structure that I have represented over here. And if I just tell you some nice, interesting facts about benzene, as you can see, benzene has carbons. How many carbons? 6 carbons. So 1, 2, 3, 4, 5 and 6. Now you're going to then rethink about, wait, we talked about cyclic structures and aliphatic hydrocarbons, and one that has 6 carbons is represented right here, cyclohexane. And how is it going to be particularly different with benzene? The difference is that as you see in cyclohexane, you have sigma bonds only when it comes to cyclohexane, because obviously it's hexane. You have the alkane, bonds, carbon-carbon single bonds. But when it comes to benzene, you have carbon-carbon single bonds as well. But there's carbon-carbon double bonds as well. So the single and double bonds are resonating among the structure, giving it an electron delocalization along this cyclic structure. So this is cyclic as well as planar. So as you can see, there's a circle that's represented inside this hexagonal structure, meaning that there's electron delocalization. So obviously if benzene has carbon-carbon double bonds, it's going to have pi orbitals. So each of these carbons have 2 p orbitals. Therefore, its 2p orbitals will be arranged in such a way that the upper lobe of one of the 2p orbitals of each of these carbons and the lower lobe of the same 2p orbitals of each of these carbons are forming a a balloon-like structure up and down this planar structure. So to represent that balloon-like lobes of the 2p orbitals of each of these carbons associated with the double bonds, I have represented it through a circle inside the hexagonal structure. So when I say I have represented, this is not a representation that I have brought up. It is a representation brought up by Kekulé. So you call this the Kekulé structure, where the cyclic planar nature is shown in this manner. So you draw benzene with the 6 carbon atoms, and it's cyclic and it's also planar. So, and it's also having its electron delocalizations on the 2p lobes above and below this planar structure. So that is represented with the cycle around the hexagon, inside the hexagon. And since these have resonating double bonds, or since there's conjugation under aromatic hydrocarbons, you're going to have the carbon joined to another hydrogen, and each of these carbons will have one hydrogen. So that means now, as you see, it will only have 3 bonds around the carbon. But that's not the case. Each carbon is having a conjugation. So there's conjugation, meaning there's resonating single and double bonds. So each carbon is also having a pi bond in itself. And then you're going to wonder, okay, if it's a pi bond, wait, it probably is going to have the bond length same as in the case of alkene, which is a pi bond between 2 carbons will have a bond length of 1.34 angstroms. And if that's the case, if it has pi bonds, it should probably have the same bond length around 2 carbons in the case of benzene. But do you see the same sort of bond length on each carbons between the 2 carbons? Not really. So when it comes to ethane, between 2 carbons you find the bond length being 1.34, and when it comes to benzene, between 2 carbons you see the bond length being 1.39 angstroms. So that particularly means that benzene, though it has double bonds, though it has a sort of unsaturation in it, it's not going to behave in the case as alkenes. So, which is why it's categorized under a certain different branch, and it's going to be completely different, show completely different reactions, have completely different characteristics than alkenes. Right. So with that, we are going to move to the classification of hydrocarbons, further talking about aliphatic and aromatic hydrocarbons. So now you have the basic idea of the structural variations among the hydrocarbons, and with that we are going to talk of aliphatic hydrocarbons on this end and aromatic hydrocarbons on the other end in a serious way. So now you know the main difference among aliphatic and aromatic hydrocarbons, but structural wise. So there are other certain properties in which you can differentiate among the two, such as saturation, chemical reactivity, which we are now going to refer one by one. So talking about structural wise, once again, both of them, they contain carbon and hydrogen as elements. They come under hydrocarbons. And when it comes to aliphatic, you may find linear, branched or cyclic structures. But the only difference among the two is that when it comes to aromatic, there's electron delocalization. And you will always get a cyclic planar structure under aromatic structures. But when it comes to aliphatic, there's no such electron delocalization, meaning electrons cannot, resonate among the bonds. They are just situated in one particular station which they are at the bond, which means they are at the bond. So when it comes to saturation, so now you know there's two types of saturation. There's unsaturation as well as saturation. So aliphatic compounds, as you saw previously, will be unsaturated as well as saturated. Where under acyclic hydrocarbons, there's saturated compounds, acyclic unsaturated hydrocarbons as well. So there could be both. But aromatic compounds are always unsaturated with their pi bonds. Unsaturated means that they will have carbon having 4 bonds around it, yet it will have less number of hydrogen atoms. So that's that with saturation. And what do you think about chemical reactivity among the two different types of groups? So aliphatic compounds are more reactive in chemical reactions than aromatic compounds. And when it comes to chemical reactivity of aromatic compounds, they're somewhat unreactive and need absolute conditions for any reactions. So the simple reason for this is that aromatic compounds are stable on their own. So that's because of their stabilization. Mainly with the conjugation and the resonance stabilization, they are already stabilized on their own with the electrons being delocalized around the structure. But when it comes to saturated and unsaturated compounds, they are anyway reactive than aromatic compounds, but also saturated compounds already have its hydrogen atoms, the maximum amount that it can hold. Therefore, they are comparatively less reactive than unsaturated hydrocarbons. Unsaturated hydrocarbons, on the other hand, are the most reactive out of all the hydrocarbons, simply because it can have more hydrogen atoms than it already has. So, for example, in the case of ethene, now in this case, it's only bonded to 2 other hydrogen atoms. And it has a double bond where, between the 2 carbons, it has a single a sigma bond and the double bond. So this double bond, the pi bond can be broken among the 2 and another extra hydrogen or another certain atom can add in simply because it's unsaturated. Same goes with the triple bonded alkynes as well. Therefore, they are comparatively highly reactive. But comparing the two, aromatic compounds are stable, so they are not very reactive, unlike aliphatic compounds. Talking about the carbon percentage of aliphatic compounds, they have a lower percentage of carbon, while aromatic compounds have a higher percentage of carbon. And sooty flame means when it burns, so when you burn aliphatic compounds, whether you will get some soot at the end of the burning procedure. So when aliphatic compounds burn, they form no sooty flame. But when it comes to aromatic compounds, when they are heated strongly, a sooty flame is observed, meaning there's remaining carbon at the end of the burning procedure. And the boiling point of aliphatic compounds, they have a higher boiling temperature than aromatic compounds, and when it comes to aromatic compounds, they boil at a lower temperature than aliphatic, hence they are more volatile. So that's the general differentiation among the two compounds, and this is the classification. So hope you got a clear-cut idea as to how the classification of hydrocarbons is done. So we will meet you in the next video with the classification of organic compounds according to their functional group. So see you soon.